All right, so let's start chapter 18. Okay, so here you will be learning about electric current, resistance, and Ohm's law. All right, so let's start with electric battery. Okay, so which is important component of an electric circuit. Okay, so you all know what a battery is. Okay, so we use battery in all kind of electronic devices. Okay, so what a battery does is it uh, transform the chemical energy into electrical energy. Okay, so a schematic diagram of a battery cell is here. Okay, I mean electric cell is here, and a battery is basically combination of several such electric cell. Okay, and here you see that it contains two plates or rods. So 2 by 2 plates, I mean this one, this. All right, yeah. So by 2 plates or rods, I mean this one and this one. Okay. So here you see that one plate is made of copper and another is made of zinc. Normally they are made of two different metals. Okay, so in another example, so here you see that one is made of carbon, okay, and another is made of zinc. Okay, so they are two different metals. Okay, we call them electrodes. Okay, so we call them electrodes, and they are immersed in some paste or solution. For example, here in this example, we use dilute sulfuric acid, and this solution or paste we call electrolyte. Okay, now how it works. Okay, so to understand how it works, let's go to here. So you see that when we immerse the electrode into the sulfuric acid, into the dilute sulfuric acid, this dilute sulfuric acid actually dissolves this zinc. Okay, this this zinc. Okay. Now, when zinc is dissolved in sulfuric acid, it basically left behind 2 electrons in the plate. Okay, and you know that the electron is negatively charged, and that's why the right-hand side plate, the zinc plate, is negative, is the negatively charged, and we call it negative terminal. Okay, or we also call it anode. Okay, so negative terminal, also called anode. Now, when zinc is dissolved in the sulfuric acid, so this solution becomes more positively charged. Okay, so more positively charged try to pull electron from the other plate, for example, from the copper plate. Okay, so when when the solution pull electron from the copper plate, it becomes more positive. Okay, because it donated already one electron. Okay, and that's why the left hand plate is positively charged. Okay, so when there is a negatively charged plate and a positively charged plate, there is a potential difference between these two plates. Okay, and you know that potential difference, when there is an electrical potential difference between two plates, there is an electrical potential energy, right? So you already learned in last chapter how the electric potential difference is related to the electric potential energy. So that electric potential energy we basically use. So you see how chemical energy is transformed into electrical potential energy. Okay. All right. So normally in triple A or double A battery, it looks like this, and this kind of batteries have a carbon electrode. Okay, that is the positive terminal. We call it cathode, and a zinc negative terminal. I mean zinc as a negative terminal or anode. Okay, and here instead of the dilute sulfuric acid, some paste are used. So some electrolyte pastes are used. Okay, and I mean, I believe most of you already see this kind of thing. Okay, all right. The next one is the electric current. Okay, so the electric current is the rate of flow of charge through a conductor. Okay, as you learn in earlier chapter, Q is the charge. So I is basically delta Q over delta T. Okay, here I is the current. Okay, so this is the current, and delta Q is the amount of charge passing through a given area in time delta T. Okay, so sometimes we instead of delta Q delta T, we just write it Q over T. Okay, it's basically the same thing. Here Q is the amount of charge passing through a given area in time T. Okay, now what is the standard international unit? So you know that this is Coulomb, right? I mean, the unit of charge is Coulomb, and this is seconds. Okay, so then the unit of current is Coulomb per second. Okay, and it has some special name, we call it ampere. Okay, and use A for ampere, and 1 amp is equal to 1 coulomb per second. Okay, and it's a scalar quantity. Okay, so many students make mistake because they think that it flows some direction. Okay, so it is a vector quantity, but it's not a vector quantity. Although it flows in some direction, it's not a vector quantity, it's a scalar quantity. Remember that. Okay, current is a scalar quantity, and in the next slide I'm going to tell you the direction of the current. Okay, so here in this table I basically show how much current is dangerous for us. Okay, for example, 1 milliamp is okay, we can feel it is not dangerous. 5 milliamp is a very small amount of current, but it could be painful. Okay, and above 5 milliamp current is very dangerous. Okay, so you have to be careful when you work with current. Okay, a small amount of current can cause I mean, much more danger. All right, so electric circuit. Now I'm going to talk about the electric circuit. A very simple electric circuit is this one. Okay, and the schematic diagram of this circuit is this. Okay, so here you see that we have a battery. So very important component of an electric circuit is a battery or the energy source. Okay, so this is the energy source and a device. So here the light bulb is a device. Okay, and this device could be anything. Okay, it could be computer, it could be your mobile phone, it could be it could be the fan. Okay, so the device is basically any electric device. Okay, and battery is the source. Okay, source of potential difference. Okay, and they should be connected by conducting wires. So here these are conducting wires. Okay, if it is not conducting, okay, then it is not a circuit. I mean, the current cannot flow through them. Okay, and if there is a broken here, if there is a broken wire, okay, if it is not completely connected, again it is not a circuit. Okay, circuit means it should have a battery, I mean the source of potential difference, it should have a um, device, and they should be connected completely, okay, with conducting wire. Okay, then we can call it a circuit. Okay, so here you see that battery symbol. Okay, in the last chapter we discussed about the battery symbol. So it is two unequal parallel line. The bigger one is for the positive terminal or the large potential, and the small one is for negative terminal or the small potential. Okay, and the direction of the current is starts from here, so it should go in this direction. Okay, okay, it starts from the positive terminal. Okay, many students make mistake. They thought that the current is the flow of electron. Okay, so yes, it has some contribution, but conventionally, okay, we use these as the direction of the current. Okay, the uh, the direction of the positive charge flow, not the electron flow. So positive charge flow in this direction, and the direction of the current is same as the positive charge flow, not the electron flow. Okay, so remember that. Okay, all right, so let me show you a circuit simulation. Okay, so here you see that we have a battery. Okay, so when switch is not closed, you know that it is not a complete circuit. Okay, because electron or the charge cannot flow. Okay, so when switch is closed, you see that electron is flowing, I mean charge is flowing. Okay, and you see that the bulb is glowing. Okay, so this is a circuit. Okay, now here you see that electron flows from negative. So you see that negative terminal is this one, the bottom of the battery. Okay, so this is the negative terminal, so it's flowing in this direction. Okay, from right to left. Okay, but the conventional current direction is opposite. So if I show you, it would be this. So you see that this is the direction of the current. Okay, it's starting from, so you see that it is going so you can say that it's starting from here. Okay, from the positive terminal and going to the negative terminal. Okay, and you see that this is the different than the electron flow. Okay, so remember that. Okay, all right, the next thing I'm going to tell you is Ohm's law. So what is Ohm's law? Okay, so Ohm's law tells us that current I that flows uh, through a device, okay, is proportional to the applied voltage. Okay, so it tells us that current I is proportional to applied voltage. So higher the applied voltage, higher the current. Okay, so let's see this in this simulation. Okay, so here the device here is basically this red cylindrical shape object. Okay, it's basically a wire. Okay, now here you see that this wire is connected with 4.5 volt. Okay, so three 1.5 volt battery, so altogether it is 4.5 volt. Okay, so for 4.5 volt, the current here is 9 milliamp. Okay, now if I increase the volt, you will see that current is increasing. So you see that current of when you are increasing the voltage, current is increasing. If you decrease the voltage, you see that the current is also decreasing, but there is no change in R. Okay, so I'm going to talk about R later. Okay, okay, so what we see in the simulation is there is a proportionality relation between V and I. Okay, so in some textbook it just written something like this: V is proportional to I, or I is proportional to V. Both are the same thing. Okay, so now we need a yeah, so let me just follow my note. Okay, so now if I want to write an equation from this proportionality, I will need a constant, proportionality constant. So here the proportionality constant is 1 over R. Okay, okay, so if I simplify this equation little bit, I will get V equal to IR. Okay, so this one or this one, both are the Ohm's law. Okay, now if I draw a graph, I mean draw a current versus voltage graph, okay, it will be something like this. It will be a straight line going through the origin. Okay, and if I determine the slope of this graph, I will get the resistance, I mean reciprocal of the resistance. Okay, so I versus V graphs, slope is 1 over R, but but if we do V versus I, okay, then the slope will be just R. Okay, so don't confuse this. In some textbook, okay, they use this. Here in this textbook we use this. Okay, all right. Now what is R? So R is a constant. So here you see that R is a 1 over R, or R is a proportionality constant. So it should be a constant. Okay, so it is a constant, and it is different for different devices. Okay, so for a particular device it is a constant. Okay, and we call it resistance. Okay, now to understand resistance, let me go to here. Okay, so here you see that a battery is connected with a, I mean a let's say a metal wire. This red cylindrical shaped thing is a wire. Okay, so this red wire is connected with a battery. Okay, now so you see that the electron, so from the negative terminal of the battery, you see that the some blue ball is going. So this blue ball is basically the electron. Okay, so the electrons are flowing in this direction. Okay, now when the electrons are flowing in the red cylindrical shape, you see that something resisting the flow of electron. Okay, so even it is a metal is a good conductor. So even the metal is a good conductor, there is something inside the metal that resists the flow of electric charges. Okay, and that is the resistance. So resistance is basically some internal property of a device or a, a metal or a substance, okay, that resists the flow of charges, electric charges. Okay, and it is constant for a device. Okay, now what is the standard international unit for a resistance? It is ohm. Okay, so ohms, and this symbol is I mean we use this symbol to represent ohms, and it is a capital omega, a Greek letter. Okay, and this symbol means omega. Okay, now you will find two types of devices. Okay, some device follow the Ohm's law. Okay, some device or some substance follows the Ohm's law. We call them ohmic substance or ohmic device. Okay, and there are some substance or device that don't follow the Ohm's law. Okay, so Ohm's law, following Ohm's law means I versus V graph is something like this, a straight line. And there are many devices that don't follow the Ohm's law, and then their I versus V graph is something like this. Okay, I mean, what I mean is it's not a straight line. Okay, if it is not a straight line, if the I versus V graph is not a straight line, that means that is not a ohmic device or ohmic substance. Okay, so what are the ohmic substances? Resistors. So I'm going to talk a little bit about resistor in the next slide. Metals. Okay, they are ohmic substance. And what are the non-ohmic substance? Diodes, vacuum tubes, transistors. These are the um, example of non-ohmic substance. Okay, all right. So even the metals are ohmic substance, but R may not be a constant if the temperature changes too much in a metal. Okay, for example, if you think about a filament bulb, okay, so here I have a filament bulb. So if you think about a filament bulb, okay, when it is glowing, okay, the temperature is too much over there. Okay, so the resistance of this is different than when it is not glowing. Okay, so that's why filament bulb is not a ohmic substance. Okay, and even here the metal, so the filament is made of metal. Okay, so normally metal is a ohmic substance. Okay, conducting wire is a ohmic substance, but when it is used as a filament, it's not a ohmic, because at low temperature, when it is not glowing, the resistance is different than when it is glowing. Okay, the same thing for the coil. Okay, but for example, the power line here, here the temperature is not the temperature change is not too much, so they are ohmic, they follow the ohmic, I mean, they follow the Ohm's law. Okay, so because of this, Ohm's law is not a fundamental law of nature. Okay, so for example, Newton's law, Newton's laws of gravitation, Newton's laws of motion, these are the fundamental law. It's valid for all. Okay, but here you see that Ohm's law valid for some substances and not for all other. Okay, that's why it's not a fundamental law of nature, but it is a description of certain class of material, for example, metal conductor, and then and whose temperature does not change too much. Okay, even if it is a metal conductor but the temperature changes too much, then you see that Ohm's law is not valid for that. Okay, so Ohm's law is valid only for certain metals when where the temperature change is not too much. Okay, all right. So now let me talk about resistors. So resistors are some device, okay, we use to control current in bigger electronic devices. Okay, and they are with some known resistance. Okay, so resistors are some device with known resistance, and we use this kind of resistors to control currents in a bigger electronic devices. Okay, now you probably see this kind of thing in an open circuit. Okay, so this is a resistor. Okay, so we use the color coding to know the value of the resistance in a resistor. Okay, let me talk about the color coding, but before then, let me tell you that in a schematic diagram, we use zigzag line, something like this, to represent a resistor. Okay, so when you see zigzag line in a circuit, that means it is a resistor. Okay, and here you see this is the battery, two unequal parallel line. Okay, now here you see that in a resistor there are several lines, several color coding. Okay, so the color coding works something like this way. So here in this table you see for each color there is some number, there is some multiplier, and there is some tolerance. Okay, so what this mean are the first two colors basically tells you about the first two digit of the value. Okay, the third color is the multiplier. So here you see there is a one column for the multiplier. Okay, so the first two digit is basically, first two color is basically first two digit, the third color is the multiplier, and the fourth color is the tolerance. Okay, so for example, here we have red and green for the first two. So the red is 2, green is 5. So the first two digit will be 25. And then multiplier is the YOLO. So YOLO multiplier is 10 to the power 4. Okay, and tolerance means the uncertainty. So plus minus. So silver is the fourth color, which is the tolerance, and you see this is 10% uncertainty. Okay, so for example, 10% of this value is these. Okay, so um, uh, the value of these resistor varies from this value to this value. Okay, that means the uncertainty. Okay, so its value is in between these two numbers. This is the lowest and this is the highest. Okay, tolerance or the uncertainty basically tells us about these. Okay, so I have a simulation here. You can see the same thing. Okay. Okay. So you can use any color coding. For example, let me use the pink for the first one, green for the second one. Okay. And for simplicity, I'm just using the brown. Okay. And yellow for the last one. So the first one, the pink is the first digit. So it should be 7. The second one is green. So it should be 75. And the multiplier is, so here 0 means 1. Okay. So 0 means just 10. Okay. I mean 10 to the power 1. Okay. If you go to here, you see that brown means 10 to the power 1. Okay. So what we expect is 5 times 10 to the power 1. Okay. So 750, right? So if I use the probe, you see that it is 0.7, and here because it is in kilo. Okay, so it shows that the resistance of this sample is 0.75 kilo, and 0.75 kilo ohm means 750 ohm. Okay, so it matches. Okay, and because it is simulation, there is no tolerance. Although we use tolerance here, there is no tolerance here. But in real life, when you do some lab, if we have something like this, you will see that the value of a resistance is not exactly what is written or what is expected from the color coding. Okay, so you have to check the tolerance also. Okay, so if it is within the tolerance, that means it is correct. Okay, all right. The next one is the resistivity. Okay, so the resistance of a substance. Okay, so for simplicity, let's just consider a OR. Okay, conducting wire. Okay, so the resistance of a conducting wire depends on several things. Okay, for example, resistance is proportional to the length of the wire and inversely proportional to the cross-sectional area. Okay, so this tells us that R is proportional to L. That means longer the wire, higher the resistance. And this tells us that thicker the wire, lower the resistance. Okay, so you can see that from here. Okay, so if I make it long, you will see that resistance decreases. For example, currently the resistance is 0.667 ohm. Okay, so in the in this white box, it's showing that resistance equal to 0.667 ohm. So if I make it long, you will see that resistance increases. Okay, so let me make it long, and you will see that the value of resistance is increases. Okay, so you see that higher the, I mean the longer the wire, higher the resistance. Okay, all right. Now if you make it thick, okay, as you know that the resistance is inversely proportional to the cross-sectional area. So if you make it big, I mean thicker, the resistance will decrease. So let me make the cross-sectional area bigger. Okay, so you see that I'm making it bigger, and you see that the resistance is decreasing. Okay. All right. So we already see that. We already see these two properties. Okay. Now, if I combine these, I can write L over A. And if I want to write an equation, I need a proportionality constant. Here, the proportionality constant is rho. Okay. And this rho we call resistivity. Okay. And this is completely the property of the material. It is different for different material. Okay. In the next slide, I have a table, and this table shows us the resistivity of several materials. Okay. And you see that the lowest value we can have for a metal wire is the silver. Okay. Silver has the lowest resistivity. Okay. And the copper is next to lowest. Okay. So even the silver is the lowest because it is little bit more expensive than copper. So we use the copper wire for household wiring. Okay. So the unit of resistivity is omega times meter. Okay. All right. Now here there is another column. It tells us about the temperature coefficient, alpha. Is very similar to the linear expansion coefficient. So remember that in chapter 13, you learn about the linear expansion coefficient, and it was also alpha, but this alpha and that alpha are two different things. Okay, one was the linear expansion coefficient, and this is just the temperature coefficient. Okay, although the unit for both are the same, but they are two different things. Okay, now over there, when you learn about the linear expansion, you see that delta L is equal to alpha L0 delta T, right? The change in length. So the new length will be original length plus delta L, right? So L0 plus alpha L0 delta T, and then L0, right? We can write something like this for the linear expansion coefficient. So similarly, the resistance and the resistivity also change with temperature, and it exactly follow the same thing. Okay, so for example, the new resistivity will be something like this: 1 plus alpha delta T. Okay, although this alpha and this alpha are two different. So this is the linear expansion coefficient, and this is the temperature expansion coefficient. I mean temperature coefficient, right? But you see that the equation is exactly same, and the same thing for the resistance. Okay. Right. And the delta T is basically the final temperature minus initial temperature. So here the T is the final and T0 is the initial temperature. Okay. So you see that this two equation tells us that resistivity and resistance depends on the temperature. When you change the temperature, resistance and the resistivity both changes. Okay. All right. The next one is the electric power. Okay, so power you already learned in physics 1, and similar to physics 1, it is the energy transformed by a device per unit time. Okay, so here energy transform basically means the potential energy, electric potential energy transformed. Okay, and we can write it PE. So power is equal to potential energy change per unit time. Okay, and in last chapter, I mean, in potential chapter, electrical potential chapter, you learn that the potential, the potential difference is related to the potential energy by this equation, right? So, very similarly, we can, so here normally we use Q for charge. So I replace Q0 by Q. Okay, because normally here in this chapter we are using capital Q. So you see that the potential energy is equal to VQ. I mean, here in this chapter we are also not writing this subscript. Okay, so the potential energy is V times Q. So the power P is equal to V Q over T. And you know that Q over T is current. So P equal to just I times V. Okay. So in an electrical, I mean, from a potential source, from a battery or from some other source, the power is basically I times the V. Okay, so I is the current and V is the voltage. Okay, and similar to the physics one, the unit is watts, and 1 watt is equal to 1 joule per second. Okay, and now if we have a resistance, and if I want to know how much power is dissipating from a resistance or a device, we can use these following equations. Okay, so let's say we have a resistance, I mean we have a resistor of a resistance R. Okay, and I want to know what is the power dissipated from that resistors. Okay, so to know that, we can use this equation. Okay, and from Ohm's law, as we know that V equal to IR, so we can use this equation. Okay, or we can also use this equation. I equal to V over R, V, so V square over R. Okay, so P equal to IV, normally we use for a source. Okay, because for a source we can find I and the potential difference, and for a resistor normally we use this equation or this equation. Okay, so for a resistor the power is I square R or V square over R. For a source it is IV. Okay, all right. Now the cost of electricity. Okay, so here I am showing a meter, electric meter. So you see that we pay bill in terms of kilowatt hour. Okay, so kilowatt hour is not a unit of power. Okay, because power's unit is watts or kilowatts. Okay, so it is not power, but it is energy. Okay, it is an energy unit. How it is energy unit? So P equal to potential energy over T. So the potential energy is equal to P times T, right? So the P is the watt or kilowatt, and time is hour or second, whatever. So you see that this kilowatt hour is the unit of energy, potential energy or any energy. Okay, so remember that this unit is the unit of energy. So we pay bill for energy, not for power. Okay, although this is not standard international unit, this is some other unit. Okay, because hour is not standard international unit for time, and kilowatt is also not standard international unit for power. Okay, so what is the relationship between 1 kilowatt hour to our standard international unit of energy? So let me show you that. Okay, by the way, 1 kilowatt hour means 1 unit in our electric bill. Okay, so 1 kilowatt hour means 1000 watt. So 1 kilowatt means 1000 watt, and 1 hour means 3600 second. Okay, so when you multiply these two, you get 3.6 times 10 to the power 6 joule. So 1 kilowatt hour means this in our standard international unit. Okay, all right. Now the next thing is the power in household circuit. Okay, so in our household, so here I show a schematic diagram. So these are the outlet you see, and they are connected in parallel. So we are going to discuss parallel and series circuit in the next chapter, little bit in details. Okay, here just remember that in our household wiring, we use parallel connection. Okay, and um, so the benefit of using parallel connection is if there is one problem in one circuit, okay, still the other will be okay. Okay, but if we connect in series, okay, if there is if there is a problem in one circuit, okay, one connection, uh, you have to repair the whole household. Okay, so that's why parallel connection is preferred in household wiring. Okay, so we'll be discussing this in the next chapter in little bit more detail, but here I want to tell you that that what happen if too many too many I mean things, too many devices are connected to our outlet. Okay, so if you use too many devices at a time, they will try to draw too much current from the power company. Okay, now too much current, this wire cannot tolerate too much current. Okay, because too much current means too much power. Okay, so too much power means so if you write this, so you see that when there are more current, okay, the power will be high, and this power basically could cause high heat, and high heat could cause firing in the household. Okay, so there is some limit. Okay, now in accidentally if you try to connect too many devices at a time, then there is a way to avoid to avoid household firing. What is that? That is the fuse. Earlier days we use fuse, nowadays we use the circuit breaker. Okay, so what is the circuit breaker? Circuit breaker is basically when um, when your household devices try to draw too much current from the power company. Okay, the circuit breaker breaks the circuit. I mean, circuit breaker disconnect the connection from your house to the power company, and you are safe. Okay, and in a circuit breaker normally we use the bimetallic stripes. Okay, and we discussed a little bit about the bimetallic stripes in chapter 13. It's basically used as the property of how um, object changes with temperature. Okay, so as you know that most of the substance, I mean especially bimetallic stripes, increases in size. Okay, when the temperature increases. Okay, and decreases in size when the temperature decreases. Okay, so by using these, circuit breaker are designed so when there are when the I mean when this system try to draw too much current, it becomes hot. Hot means high temperature. High temperature means the increase in the bimetallic strip. So when the bimetallic strip is increased, so they are designed in such a way that it disconnect the circuit. Okay, all right. So the next and the last thing is the alternating current. Okay, so far we basically learn about the direct current or DC current. DC current means the current that we get from the battery. Okay, so in a battery, if we plot the current versus time graph, it is a straight line. Okay, a constant current we get actually from a battery or the direct current. Okay, on the other hand, alternating or AC current is changing its direction. Okay, in some time it goes in positive direction and sometime it goes in negative direction. So you see that alternating current is something like this. Okay, so you see the positive part, negative part. Okay, positive part, negative part. Okay, so the the current we use in our household that we get from the power plant is basically alternating current or the AC current. Okay, so it's basically something like this. So let me change it with this. Okay, this means the alternating. Okay, so you see the direction of current changes. So sometimes it is toward right, sometimes it is toward left. Okay, and here you see that the frequency is 2 hertz. Okay, that means it changes 2 times in 1 second. Okay, now you may ask the question why we cannot understand. So here we can understand that it is changing its direction, right? And the bulb is going bulbs I mean this glow is going in one direction in one time and another direction in another time. So here it is easily here we can easily understand it. But you may ask the question why we cannot understand when a bulb is glowing in our household. Okay, the answer is, so here it is only 2 hertz. That means 2 times in 1 second. I mean, it changes 2 times in 1 second. But in our household, it changes 60 times in 1 second. Okay, so 60 times in 1 second is too much that our brain cannot analyze it. Okay, that's why we see a continuous. Okay, so the number in Canada and the United States is 60 hertz. In most other country it is 50 hertz. Okay, that means in their country it changes 50 times in 1 second. Here or in Canada it changes 60 times in 1 second. So 50 or 60, whatever the number is, it is too much for our brain to analyze, and that's why we see it's continuous. Okay, now let's try to understand the mathematical explanation of this alternating current. Okay, so you see that this is very similar to the simple harmonic motion, right? So in simple harmonic motion chapter, you see that if we have a graph something like this, we represent it using the sine or cosine cosine curve, right? So similar to that, we are going to use the sine curve or sine function or the cosine function to do this. Okay, so for example, the alternating voltage, we use this equation v equal to v0 sine 2 pi ft or v0 sine omega t. So here f is the frequency. I believe you already remember it. So this is the frequency and this is the angular frequency. Okay, so angular frequency omega is equal to 2 pi ft. Okay, and f is the frequency. Okay, and v0 we don't call it we don't call it amplitude here. Okay, instead we call it peak voltage. So this is the peak voltage or this is the peak voltage. Okay, so here the green green curve is the voltage graph. Okay, so here you see that v0 is this one. Okay, either this one or this one. So V0 is the peak voltage and it is very similar to the amplitude in simple harmonic motion. Okay, now I want to know what is the current. Okay, alternating current. Okay, so the alternating current is okay, so you know that I is equal to V over R, right? That is the Ohm's law. So if I substitute the value of V0 sine omega t r, okay, I get something like this v0 r sine omega t. Okay, so I can write this as the peak current. Okay, I0 sine omega t. So here I0, which is equal to V0 over R, is the peak current. Okay, I0 is V0 over R is the peak current. Okay, so you see that the frequency does not change, but the amplitude changes, and that's why the graph looks like this. So here you see that when the voltage is zero, current is zero. When the voltage is maximum, current is also maximum, but the maximum value are different. Okay, that's because the amplitudes are different. Okay, all right. Now then, uh, what is the power? Okay, so what is the power in alternating current? Okay, so the power, you can use several equation. Okay, you can either use IV, you can use I square R, or V square over R. Any equation will be fine, but let's use this one. Okay, okay, so I square R. So I square R means then I0 square and then sine square omega t R, or I0 square R sine square omega t. Okay, so the P is something like this. Okay, but when we deal with alternating current, we are not interested on the this power. Okay, we are interested on average power. Okay, but before I go to the average power, let me show you the behavior of this graph. Okay, so so here you see that the behavior of this power is something like this. So you see that it's all above the zero line, and that makes sense because it is a square. Okay, square means it's above the zero here. Okay, and and you see that so because this is I0 R sine square omega t. Okay, it looks like this, and the maximum peak value is here I0 R. Okay, so you see that I0 R is this value. Okay, but yeah, as I told you that we are interested on the average power when we deal with alternating current. Okay, so what is the average power? Okay, so average power is this. Okay, so R is a constant, I0 is just another constant, it's just the amplitude, so we cannot take the average of these. Okay, but sine square omega t, we can take it average. Okay, and in trigonometry, if you take the average of a sine square function, it's basically very simple. It is basically equal to half. Okay, sine square or cosine square, our average is half. So what we get is half I0 square R. Okay. Similarly, you can show that P equal to half V0 square over R, or half I0 V0. Okay. Now, if I compare it with the DC power and AC power, you will get it comparison. Okay, so let me do it. Let me write down, okay, side by side. So let me first erase this. So in DC current, you see this equation IV, and then I square R, and then V square over R. And here in AC current, the average power is half I0 V0 half I0 square R half V0 square over R. So here you see it's very similar, but with a half. Okay. And now these are the peak current and peak voltages. Okay. All right. Now we can say that as we are interested on the peak value for the power, the average value for the power, why not it for the voltage and current? Okay. So for voltage and current, if we take the average value, it will give you 0. Why? Because you see that some part is above the 0 and some part is below the 0. And it's basically exactly same part. So when you add them together, you get 0. Okay. So that's why we are not interested on the average value for the alternating voltage and alternating current. Okay. But we are interested on something else. Okay. And we call it root mean square or RMS value. Okay. And I believe you remember what the root mean square means, at least mathematically, from chapter 13. Okay. While we are learning about the kinetic theory, we derive an equation for root mean square speed. Okay. It's very similar. So what we have to do, we have to take the square of a quantity and then take the mean of it and then take the square root. Okay, that is the root mean square. Okay, so let's do it. Let me go back to the whiteboard. Okay. So let's start with V0, I mean V. So V is V0 sine omega t. Okay, so V square is this, right? V square is equal to V0 square sine square omega t. So what is the average of V square? Average of V square. So we cannot take the average of the peak value. So average of V square is this, but this is equal to half, right? So average is this half V0 square. And the same thing you can show that I square average is equal to half I0 square. Okay. So what is the then VRMS? The RMS voltage. This is square root of this. And this is equal to square root of half V0, or the value of square root of 1/2 is just 707. Okay. So VRMS is equal to something like this, and same thing for RMS. Okay. Now, why we need VRMS and IRMS? We need VRMS and IRMS because the power outlet, okay, so normally the household power outlet in United States and Canada gives us 120 volt AC, okay, and this 120 volt AC means the RMS value, okay, so that's why we need the RMS value. Okay, because you may in some numerical problem you may say you may be given that a device is connected to the power outlet of your house and that is giving you 120 volt AC. Okay, so question basically tells you something like this. It will not explicitly tells you that it is RMS value, but you have to understand that when you connect your device to the power outlet, that is the I mean RMS value. Okay, so 120 volt the power outlet gives us is basically the RMS value. Okay, so that's why you need it. Okay, now Now here from this equation, you already see what is the relationship between the RMS value and the peak value. Okay. So sometime the power the average power is calculated in terms of the RMS value. So in terms of the RMS value, it will be RMS V RMS. Okay, and that's because P, one of the equation was half I0 V0. Okay, similarly, we have this I square RMS R and V square RMS over R. Okay. Okay, and that's because of this equation. If you substitute the value of VRMS and IRMS by solving V0 and I0, okay, you can get these equations. Okay, so you see that in terms of the VRMS or IRMS, the average power equation are these. In terms of the peak voltage and current, the equations are something like this. Okay, sometimes you may see that the peak voltages or peak current are important. Sometimes you will see that IRMS or VRMS are important. So whatever you need, you can choose from these sets. Okay. All right. So the last thing, just to tell you, I already mentioned at some point, the value we get from our outlet is 120 volt. Okay, so that is the VRMS. Okay, now if I want to know what is the peak value for that, you can just use this equation. V0 equal to VRMS over 0.707. Okay, that's basically you solving this equation. Okay, now if you plug the value of VRMS, 120 volt over 0.707, you see that the peak voltage in our household is 170 volt. All right. So with this, I am going to stop. And in the next class, I will be talking about, I will basically solve some classwork problem.